Hello, dear students. So, I am Vikas Agarwal, and I'm here to bring you the next series of Basics to Advanced. So, this is a series for preparation of NSEJS 2025. And what we'll be doing in this series, let me tell you that, and then I will tell you that what we have done till now and what we will be doing in today's session. So, this is the sequence in which we are going to cover the topics. We are in this stage right now. We are doing the basic mathematics, and after that, we will begin the chapters of physics. So, in basic mathematics, we need to cover trigonometry, coordinate geometry, determinant function, differentiation, and integration. So we have done all these things, and today we'll be doing differentiation. All right, so that would be the content of today's session. In today's session, we are going to learn how to differentiate, and then we are going to talk about what is the meaning of differentiation. Like, why do we do that? Okay, or when we are forced to do that, when we are required to do that. So, uh, before I start today's proceedings, guys, I would like to tell you that we have opened a new channel specifically for Science Olympiads. Okay, the name of the channel is Vedantu Science Olympiad. That's a YouTube channel, and here, correspondingly, we have opened a Telegram channel also. Here is the link of the Telegram channel, and I would request you guys to please find this channel on YouTube and subscribe to it because very soon we will start posting content here also, and the content that we will post here will be for NSEJS and other senior Olympiad. On that note, let's begin, guys. So the first question or the first thing that we need to address is that what exactly is differentiation? Okay. Now, to answer this question, let me write something on the screen and you tell me whether you can give me the answer to this question or not. For example, suppose if I write 5 and 2 and then if I ask you the answer. All right. With this information, you will probably not be able to answer. Okay. But the moment I put a sign here, now you will be very quick to answer 10. Okay. To give me the answer as 10, which is correct also. So let's understand what exactly happened here. Like until I wrote this symbol, you were not very clear with what would be the answer, but the moment I put a symbol here, okay, you knew exactly what you should be doing, and you then did it, and then you gave me an answer. So let's understand what happened here. So let me start by telling that what I wrote here is called an operator symbol. Okay, it is an operator symbol which indicates the operation of mathematics. All right, it is universally chosen to denote the operation of multiplication. Okay. Now, this is something, the operation of multiplication. You have been taught in your junior grades, very young, when you were very young, you were taught this operation of multiplication. Okay. So it denotes operation of multiplication. I missed the word operation. Okay. So, and the so multiplication is an operation. To denote that, we have an operator symbol. Okay, and the entities on which the operation is performed, they are called the operands. Okay, they are called operands. Okay, and this is your result. This is your result of the operation. Okay, up until now in mathematics, primarily there are four operations that you have learned, and those four operations are addition, and it has got its own operator symbol. This is the symbol. Subtraction, it has also got its own symbol. Okay, you have learned multiplication and you have learned division. So primarily these are the four operations that you have learned. Okay, each of these operations require two inputs or two operands, and when you go to get those two operands, you are able to calculate an answer. Okay, this is what you have learned until now. Now, going forward, the mathematics that involves these four operations only becomes inadequate for us. We need more operations. We need fresh operations, more operations. And those two new operations are differentiation and integration. So, first, understand what they are. So, they are two new operations that you are going to learn. So, obviously, if you can recall your childhood days, I'm not sure how many of you will be able to do that, but those of you who can, you remember that each time a new operation was introduced to you, it felt like it is extremely difficult to learn it. Okay, like when addition was introduced, you started with adding single digit numbers, then two digit number, then three digit number, then I'm sure you learned in your school adding four and five digit numbers also. And once you did that, you realize that the number of digits don't matter anymore. Like even if I give you a 10-digit number, you will still be able to add two 10-digit numbers. So after a point, you become confident enough to deal with any level of complexity. Okay, then after addition, you must have learned subtraction, and then came multiplication. When came the multiplication, remember how you learned to multiply. Like to be able to multiply, you had to learn the tables. Remember your childhood days that to become good in multiplication, you were made to remember the tables, the table of 2, 3, 4, 5, 6. I'm pretty sure that you have learned that in your childhood days. And now you can, if you look back, you will agree with me that those tables are essential to learn the operation of multiplication, to become good at using the operation of multiplication, and not only multiplication, at using division as well. Okay. So after multiplication, again, if you can recall your experience, initially it would have been difficult. Even multiplying, two-digit number would have been very difficult. But later on, you learned the art of multiplication. And now, even if I give you two five-digits number to multiply between them, to multiply, you will be able to do that, and you will be able to get to an answer. Okay. Now you're supremely confident about multiplication. Same thing happens with division. Okay, and you again think about it and tell me whether you agree with me or not that when you started learning division, it was more like that whatever tables you learned for multiplication, they were coming to rescue you. You were essentially using those tables to divide as well. Okay. Now, if you can recollect your experiences of learning multiplication and division, similar thing happens when we learn differentiation and integration. All right, what do I mean by that? So just as you learned a lot of tables to become efficient in multiplication, and learning a few tables, for example, learning tables of numbers till 10 or 12 maybe, learning those tables enabled you to multiply even higher number. Like you might have learned table till 12 only, or till 15 only, or till 20 only. Yet, if I give you three digits number to multiply, you will be able to do that. I'm very sure of it. Not that you learned the table of that three-digit number and yet you will be able to multiply, because you learned some basic tables and then you learned the art or the way to use those basic tables to deal with more complicated numbers. In differentiation, we do similar thing. We will first understand what differentiation is, what is the operator symbol, and etc. etc. Then listen to this very carefully. We will learn a set of formulae. We will learn a set of formulae, very simple formulae, all right, similar to the simple tables that you learned. And then we will learn some rules. Okay, using those simple set of formulae and those rules, we will be able to do more complex questions. Okay, and we'll be able to do any question regarding differentiation. Say again, similar to what you did in multiplication, you learned some basic tables, and then no matter how long a number I give you to multiply, you will be able to do it. Yeah, you will take time, but you will do it. So same goes with differentiation. You learn a basic set of formulae, then you learn a set of rule, and using those formulae, using those rules, you come to know that what you need to do in more complex cases, and no matter of complexity will then be able to stump you. Okay, so that is about it. Okay, and as again, you use when you learn division, you realize that it is the reverse of multiplication, and the same formula is getting used in the reverse manner. In the similar way, when you will learn integration, it is the reverse process of differentiation. Whatever you will learn in differentiation, that will be we will reverse that so that we can do the integration part. So now, why we need to differentiate and why we need to integrate, that will come later. Again, similar to what you have learned in your junior grades. You learned adding and multiplying first, and then you found their application. Like then you discovered that, oh yeah, these are operations which are useful for us. Which are used in everyday life also. Differentiation may not be used in everyday life, but yeah, it is used when you study physics on an everyday basis. So, and therefore we are discussing that in physics subject. Now, coming to what differentiation is, or so guys, differentiation is an operation. It's a new operation that we are going to learn. Okay, so let's first learn the operator symbol of differentiation. So operator symbol of differentiation is a bit complex. It's not as simple as multiplication or addition or division. It involves the alphabet D. Okay, it involves the alphabet D. We write D by D. All right, this like just as how we write the ratio. So D by D, and then we write something in front of this D. We can write it using the we generally write it without using the brackets. Okay, I have made those brackets to make you realize that there should be something there, like that's a blank space. Okay, if I don't write it, my entire screen is blank. Okay, so I'm making this bracket to make you realize that there should something should come there, and again something should come here also. Okay, so again I'm making the bracket to make you realize that something should come there. That's a blank space. Okay, now whatever we write here, okay, whatever we write here, uh, you can choose any alphabet for now. Let's say I wrote a P here. Okay, so if we write a P here, so D by dP, I'm yet to fill the upper bracket. I'll do that later on. But if I write only till this part, this would be read as differentiation, differentiation of, differentiation of whatever we have planned to write here. I'm leaving it blank for now. So differentiation of whatever we plan to write here with respect to P. Okay, with respect to P. So differentiation of whatever we write here, for example, if I write a Y here, then it would be differentiation of Y with respect to P. Okay, so if I write dy by dx, then how will we pronounce it? How will we speak this mathematical language? We will pronounce it as differentiation, differentiation of Y with respect to x. Okay, so this is the representation. This is the operator symbol. Okay, and this symbol involves two operands, y and x. Okay, so this symbol involves two operands. There's one more thing I would like to tell you. Differentiation is also called derivatives. Okay, so we can read this as derivative of y with respect to x. Okay, so that is the first thing, that is about the operator symbol. Okay, next let's talk about something else. So guys, you will be able to differentiate y with respect to x. Okay, uh, only if y is a function of x, or in other words, y depends on x. So dy by dx uh, has got meaning, or it basically means that you can expect to do something. Okay, only if y is a function of x. If y is not a function of x, dy by dx is simply zero. Okay, so remember this, that you are trying to differentiate anything with respect to something, then this, whatever you're writing in the numerator, that should be a function of what you're writing in the denominator. All right, so that is one thing that you need to remember. Okay, okay, if it is function, then what to do? So for that, I'm going to tell you some formulae, okay, and you need to remember those formulae. So I'll start by telling that what happens if we try to differentiate a constant. Okay, so the derivative of a constant, derivative of any constant would be zero. All right, so I'll give you some examples on this. For example, if I differentiate, let's say 10. Now 10 is a constant. If I change x, that doesn't change the value of 10, so that would be a zero. Okay, let's say if I ask about differentiating, let's say ln3. ln3 is also constant. If I ask about differentiating the value of sine 60, now sine 60 is a fixed value. We know it's root 3 by 2. That would also be zero. So differentiation of any constant with respect to anything is zero. So differentiation of a constant is always zero. Okay, now that is one thing. The second thing that you need to remember, that is quite easy. Differentiation of something with respect to itself is always one. Okay, differentiation of something with respect to itself, it's always one. So again, this is something that you should keep in mind. The third point that you all need to remember, now I'm giving you a more general formula. Differentiation of a polynomial function. This is called a polynomial function where x has got some power, some number is written as the exponent of x. Okay, so this is n times of x raised to power n minus 1. So once you have carried out the differentiation, this is what you're going to get. Let me give you some examples on this. So uh, example is, for example, d by dx of x raised to power 7. Okay, so here we can see that n is 7. So that would be 7 times x raised to power 6. Okay, let me give you more example. D by dx of x cube. This would be 3x square. Let me give you more example. D by dx of x raised to power 3 by 2, let's say. So that will be 3 by 2 x raised to power half. d by dx of, let's say, 1 upon x raised to power 4. This can be written as d by dx of x raised to power minus 4. So understand that in going from this step to this step, I did not differentiate. I just wrote what was given to me in an alternative manner. Now I will finish the differentiation. So minus 1 will come in the numerator. The power will reduce by 1 and therefore it will become minus 5. So the outcome would be minus 4 divided by x raised to power 5. So I hope you get the differentiation of a polynomial function. So this is the third formula that we've written. Now we will write a fourth formula. So the fourth formula would be, we'll write differentiation of trigonometric ratios. Okay, so d by dx of sine x. Okay, d by dx of sine x would be cos x. You have to remember this, everyone. D by dx of cos x would be minus sin x. Now, when I tell this to the student, many students say that's a समझ नहीं आया. Like they say, sir, I did not understand that if the differentiation of sin x is cos x, then how can the differentiation of cos x become minus sin x? It should be minus plus sin x. Why? Why? Nobody told us that. Like you don't know anything about differentiation. Why are you arguing like this? If you're thinking like this, who said that the result needs to be symmetric? Okay, like I never said that if you differentiate this and you get this, so if you differentiate this, you should get, like, what is the logic here? Okay, no one said that. Okay, we are yet learning, and there's nothing like this. I told you that if you differentiate A and you get B, then differentiating B will give you A. That is nothing like that. Okay, so don't give this argument. So, from where are we able to, like, how come we know these things? Our mathematician friends has given us this formula, and they've asked us that you use this formula, and we are doing that. Okay, so continuing, d by dx of tan x, d by dx of tan x would be sec square x. Okay, d by dx of sec x, this would be sec x into tan x. Okay, then I think for two are left. So d by dx of cot x. Okay, this would be minus cosec square x. See this. Um, mm, yeah. Okay, and then d by dx of cosec x. This is minus cosec x into cot x. So these are the six formulas that you have to learn. Okay, please learn all of these. Okay, so that was the derivative of the trigonometric function. We'll use them in a short while. Next, we come to the derivative of, let's say, exponential function. So, d by dx of e raised to power x is e raised to power x itself. And if we go a bit more general, instead of e, if I'm willing to use any other number, let's say a, okay, so that would be a raised to power x into ln a. Okay, so this is, so you see that if we replace a by e, then this becomes ln e. Ln e is 1. Okay, so that is for the exponential function. Guys, understand this, that x raised to power 5 and 5 raised to power x, they are different. This is called polynomial function, where x is in the base and the power is a number. Here, the base is a number and x is in the power. So these two are different. Okay, these two are not same. Okay, this is polynomial and this is exponential. Now, logarithmic function d by dx of ln x, that would be 1 upon x. Okay, so yeah, that should be good enough. So these are some formulas that we have written. For now, these formulas are good enough. Now let me tell you some rules. Okay, some rules, and then rules along with the formula is something that we are going to practice. Once we learn them properly, we'll be able to differentiate anything. Okay, so the first rule is that if you want to differentiate a function which has been multiplied with a constant, you can pull out the constant outside and then you can differentiate. Obviously, this you may not have understood this one. Let me give you an example. So, for example, if I ask you to differentiate 10 times of sine phi, you can pull out 10 and you can say that, okay, let me differentiate the remaining one. Why? Because x is a constant. So, whenever inside the differentiation symbol, if you see any constant, which is multiplied with something else, you can pull it out. Okay, so the answer would be 10 times of cos x. See, differentiation of sin x is cos x, so that's why we are getting it. Okay, let me give you more examples. So let's say d by dx, okay, of 10x square. So again, you can pull out 10 as the common quantity and then d by dx of x square. So that would be 10 into 2x. Okay, getting it. So this will become 20x. So This is the first rule. Okay. Now I'll go to the next rule, rule number two. So this rule says that if you have to differentiate a function that you obtained by adding or subtracting two functions, getting it? So if we add two functions of x, we get a new function of x. If we subtract two functions of x, we get a new function. Okay, in such cases, you can differentiate first and you can add or subtract them later on, whatever it is asking you to do. Okay, so I'll give you an example. Example, d by dx of sine x plus x cube. So what you can do, you can write d by dx of sine x separately and then d by dx of x cube separately. So this will become minus cos x and this will become 3x squared. Check this. I hope everyone is getting this. Hmm. Let's see some more examples. For example, d by dx of x raised to power 4 plus x cube. This will become 4x cube plus 3x square. Okay, and the same thing can apply for a difference also. For example, d by dx of let's say 1 upon x square plus sine x minus ln x. Okay, so if I were to differentiate this, differentiation of 1 upon x square will become minus 2 upon x cube plus cos x and then minus 1 upon x. Differentiation of ln x is 1 upon x. So this is the second rule. Now, again, this is quite easy to use. Now I'll go to third rule, which might be a bit confusing. So generally we assume that if second rule is true, and since this is second rule, then if we are asked to differentiate product of two function, students generally assume that differentiating the first function and differentiating the second function and then multiplying them will do the job. But guys, no, that is not true. So let me first do give you a cautionary note that this would be wrong. Please don't do this. Okay, now let me tell you that what would be the correct way to do it. So d by dx of product of two function will be written as first function into differentiation of second function plus second function into differentiation of first function. So this is what you have to do. Okay, let me demonstrate with some examples. So suppose we are asked to differentiate the product of x raised to power 5 and sine x. Okay, so you can treat x5 as the first function, and then differentiation of sine x will become cos x, and then you can write sine x as it is, and differentiation of x raised to power 5 will become 5x4. Further simplification is up to you. If you want to simplify it further, you can do that. If there are options, you want to transform this into one of the correct options, you have to do a bit of mathematics. For example, in this particular question, you can pull out x raised to power 4 as the common quantity, and then you can write x cos x plus 5 times of sine x. So this is the product rule. This is called as the product rule. Okay. And finally, we have another rule, the quotient rule. So d by dx of y1 by y2. Again, let me first give you a cautionary note. This is not allowed or this is not correct. Okay, this is not correct, guys. So, what is the correct way to go about this? You first write the denominator, that is y2. You differentiate the numerator, then minus of numerator into differentiation of denominator divided by the square of denominator. Okay, let me demonstrate. This is the formula. You have to learn it, guys. Whatever formula I'm writing, you have to learn this formula. So let me demonstrate now. So d by dx of, let's say, I write sine x divided by ln x. Okay, so this will become ln x, that is denominator, into differentiation of numerator. So that would be, let me write it first. So d by dx of sine x, okay, and then minus numerator into differentiation of ln x divided by square of denominator. Now let's finish it. So ln x multiplied by differentiation of sin x, that's cos x. Okay, minus sin x into differentiation of ln x, that's 1 upon x. Okay, divided by ln x square. So this finishes the differentiation. So that is the quotient rule for you. Okay, let me also demonstrate one more example on quotient rule. Suppose I write sin x by cos x. So again, this is ratio of two function. We know that sin x by cos x is tan x, and derivative of tan x. I made you learn that as a standard formula. So derivative of tan x would be sec square x. Let's see what happens when we use quotient rule. So this will be written as denominator into differentiation of numerator. Let me directly do the differentiation now. So differentiation of sin x will become cos x. Okay, so it will become cos x, and then minus numerator into differentiation of denominator, that is minus sin x, divided by square of denominator. So you can see here it becomes cos square x plus sin square x, that is 1 upon cos square x, that is same as sec square x. So we got the formula. Okay, so this is how we differentiate the ratio of two functions. Okay. Um, Now, let me give you an example in which we are using multiple rules together. So, watch this, everyone. So, 10 sine x plus 5x raised to power 4 divided by, let's say, 6 ln x plus um, 4 times of e raised to power x. So, we want to differentiate this. Now, this looks very daunting. So, let me do it. So, I'll first write denominator. So, 6 ln x plus 4 times of e raised to power x, and then I will differentiate with numerator. So 10 sin x will be differentiated. I will pull 10 out, and then sin x, differentiation of sin x is cos x. Differentiation of this will become 20 times of x cube. Okay, then minus of 10 numerator. Okay, minus of numerator into differentiation of denominator. So that will become 6 by x plus 4 times e raised to power x, and then this entire thing will be divided by the square of the denominator. So, okay. Guys, of course, I will share assignments in the description of this session so that you can practice differentiation. So this was the fourth rule that we did, and now comes the fifth rules. Okay. Now comes the fifth rule, which is called as the chain rule. It is a very interesting rule, guys. So I'll tell you what this rule says. So suppose if we want to differentiate, let me directly give you an example and then I will write it. So suppose you want to differentiate sin x, you know that the answer would be cos x. Now compare it with the case when instead of x, I write another function of x. For example, I write d by dx of sine, and then instead of x, let me write tan x. So where x should have been present, I wrote a function of x. Here, instead of x, I'm writing another function of x. In such cases, what you have to do, whatever you would have done, if x would have been there, you do that. So if x would have been here, I would have written cos x. So I will write cos of tan x. Okay, and then you multiply with the derivative of tan x. Like whatever you were forced to consider as x, you have to multiply with derivative of that. So the answer would be cos of tan x into sec square x. All right, so this rule is called chain rule. This rule is called chain rule. Um, all right, so let me give you another example. So suppose if I ask you to differentiate x cube, your answer would be 3x squared. But what if I ask you to differentiate instead of x, let's say I'm writing sine x. So what if I ask you to differentiate sin x cube? The answer would be, watch this, 3 times of sin x square. Do you notice this? That wherever like x was written, instead I have now sin x. So the same thing I did. But now I can't just end it here. I need to multiply with the derivative of what I assumed as sin x. I assumed sin x as x. So differentiation of sin x will be there. So the answer would be 3 sine is square x multiplied by derivative of sin x, which is cos x. So that would be your answer. So this rule is called chain rule. Okay, this rule is called chain rule. How do we express chain rule? Suppose we are differentiating, uh, we are trying to differentiate y with respect to x, but y is a function of something else. Let's say we are forced to differentiate y with respect to y1, then we multiply y. So, for example, in this example, y1 was sine x. Okay, y1 was sine x in this example. Okay. In any case, if you don't understand this way of writing, you understand the gist of it. Okay. Let me give you one more example just to ensure that you are getting it absolutely clearly. So d by dx of what should I take now? Okay. Okay. Um, 10x cube plus x square. This entire thing is raised to power 7. So we want to differentiate this. Okay, so the first thing that I will do, I will assume this entire quantity as x. So I will write 7 and then whatever I have assumed as x, I will write it and then the power of this will become 6. Now I will multiply with derivative of whatever I treated as x. I treated 10x cube plus x square as x. I have to multiply with derivative of that. Let's finish it now. So 7, then 10 raised to power x cube. Okay, 7x cube plus x square raised to power 6 into. Now, what is this? So, this will become 10 times of derivative of x cube. So, that is 3x square plus derivative of x square is 2x. Okay, so now you can just simplify it. Whatever you like, you want to simplify it, you can do it. Okay, so this is how we have to use these five rules. Okay, now there is something else called as the differentiation of parametric form. So, what exactly is parametric form? Let me tell you that. So, suppose we have been given a function like this. So, y is given as a function of t, and x also has been given a function of t. Okay, so understand this. Every time you change x, you will change t, and every time you change t, y also changes. So we have expressed an indirect dependence of y on x. So y is still a function of x, but we are expressing that dependence by using a parameter. The parameter is called t here. T is the parameter. So every time you try to change x, t changes, and if t changes, y also changes. So indirectly y is a function of t, and therefore we can talk about the derivative of y. We can talk about dy by dx, that is meaningful thing. How to do that? You can differentiate y with respect to t, and then you can divide the derivative of x with respect to t. So in the present case, it would become 3t square plus 2t divided by 2. All right, derivative of y with respect to t divided by derivative of x with respect to t. So this is how we differentiate the parametric form. Okay. Now there are a few other things that I must talk about. So the different representations. Okay. So see, let's say y was x raised to power 3 plus x square, something like this. Now, if I ask you the differentiation of y, you will say 3x square plus 2x. Now see that this is itself a function of x, and therefore, if I want to talk about the differentiation of this, then that would not be wrong. So if I say that I want to differentiate dy by dx itself, I want to differentiate this with respect to x. So d by dx of dy by dx, this is called the second derivative. Okay, this is called second derivative of y with respect to x. That means you have to differentiate twice. Okay, or this is also called as the double derivative. Okay, this is also called as double derivative. So in the present case, it will become 6x plus 2. Okay, it will become 6x plus 2. And there's one more thing I want to talk about. Uh, second derivative. Second derivative is also denoted as d square by dx square of y. Please understand where you have to put this 2 on d and on x. Okay, on d and on x. To highlight this, let me give you an example. Okay, let me give you a very simple example. Suppose y is x square, or let's say 2x square. Okay, now evaluate the following. If I ask you to calculate dy by dx, what will you do? If I ask you to calculate dy by dx of y square, what will you do? If I ask you to calculate dy by dx whole square, what will you do? Okay, if I ask you to calculate d square y by dx square, what will you do? So try this out, everyone. I will then finish it, or you can pause the video and then later on you can see the answers. So I'll give you the answers. This would be 4x. Okay, this would be d by dx of y square. So 4x raised to power 4. So Y square is 4x raised to power 4. So it will become 6x cube, 16x cube. This will be dy by dx square. Dy by dx was 4x, so 4x square. So this is 16x square. This is second derivative of y. So the first derivative of y was 4x, so the second derivative will become 4. So you see, all of them are coming out something different. So understand the representation, guys. You need to understand the representation well. Okay. Now, there is another thing that I want to talk about. Sometimes what will happen, like let's say y is given as x cube plus x square, and the question says calculate calculate dy by dx at x equals to 2. What does this mean? This means that you first calculate the value of dy by dx. Okay, so you will get an expression, and then you substitute x as 2, and that is represented by drawing a long line alongside dy by dx and putting x equals to 2 at the subscript. So 3 times of 2 square plus 2 into 2. So this will become 3 into 4, 12 plus 4, that is 16. So when the question is asking you to calculate the value at some specific value of x, what you have to do after differentiating whatever result you are getting or whatever function you are getting, in that function you have to substitute the value. All right, so guys, what I have told you here is everything about differentiation, like how to differentiate, like what are the formula that you need to remember, what are the rules that you need to remember. Of course, you will need a bit of practice to not a bit of practice. You will need a lot of practice to become very good at differentiation. Whatever there is to be told, I have told you that. Now you need more and more practice. Okay, so this is regarding differentiation. Now I will move to the second part um, of today's session, which is meaning of differentiation. What does differentiation represent? What does it mean? So let's talk about that. So differentiation makes sense only when y is a function of x. Now, to understand this better, let's take an example and let's try to understand what is going on. Okay. So if I write y as x square, that's a very simple function that I've chosen. Okay, if y is a function of x, you will agree with me that whenever we try to change the value of x, there would be a change in the value of y as well. All right, I'm pretty sure that you will agree with me. Okay, now guys, uh, let's do one thing. Let's try to find out various values of y corresponding to the various values of x. So I'm going to make a table. If I choose x as 0, I get y as 0. If I choose as x as 1, I get y as 1. If I choose x as 2, I get y as 4. If I choose x as 3, I get 9. If I choose 4, I get 16. If I choose 5, I get 25, and so on. Okay, you can continue making this. In fact, you can keep x as 1.5 also, 2.5 also, 3.5 also. In fact, you can choose more values in between these values. For example, you can go with 1.1, 1.2, 1.3, 1.4, 3.1, 2.1, like this. So the more values you choose, the longer this table gets and the more set of ordered points you get. And once you have got enough number of points, you can then make a graph. You can even go for negative values of x. So when you make a graph, after obtaining enough number of these values, you will get a graph like this. Okay, you will get a graph like this. We call this graph as parabolic. So that's a different story. So what we understand is that y is a function of x. We can make a graph of y. That's okay. Now let's select 2 points here. Let's select, let's say point A here. Let's say point B here. Let's say point C here. Something like this. Okay. So we can see that the x corresponding to A. This would be the y corresponding to A. This would be xb, like this coordinate, okay, and this would be yb, okay, this would be xc, and this would be yc, okay. So when we are changing x, in general, y is changing, okay. Now let's talk about something called as um, rate of change of y with respect to x, okay, y with respect to x. So if we agree that every time we change x, we can expect a change in y, the next question could be that how fast is y changing? For example, every time I have to change x, let's say if I change it by one, okay, by 1 unit. what is the corresponding change in y? How fast is the y changing? For example, if you notice this table, when I changed x by 1, y also changed by 1. But next time when I increased x by 1, y increased by 3. So the change in y became faster. More change happened. When I changed x again by 1, I made it 3 from 2. That's a change of 1. The change in y became 5. Okay, so the changes in y is becoming greater and greater for corresponding to the same change in x. So we can talk about the rate of change, that how fast y is changing when we change x. Okay, so we can talk about that. So that is called the rate of change of y with respect to x. Okay, now there are two ways to define the rate. One is called the average rate, and the other is called the instantaneous rate. Okay, so we'll talk about instantaneous rate later on. First, let's talk about average rate. So, whenever you want to talk about average rate, you need to specify an interval. Okay, you need to specify. Now, what does that mean? This means that if I want to talk about the rate of change of y, I need to mention from to, like, from where to where. For example, if I want to talk about, average rate of change of y between x equals to 2 and x equals to 5. So this is called an interval. I specified when x changes from 2 to when x changes from 5. So this is called average rate of change. And not only that, let's see, like, if I choose this as 2 and this as 5, correspondingly ya will become 4, and yc will become 25. So how do we define this rate of change? How do we define this rate of change? So this rate of change, okay, let me go to the next page now. So average rate of change is defined as change in y, or change of y in chosen interval divided by change of x in chosen interval. So in our previous example, y changed from 4 to 25. So change in y is 25 minus 4. And corresponding change in x is how much? X changed from 2 to 5. So it is 5 minus 2. So the rate of change would be 21 by 3. So that is about 7 units. All right, so this is called the average. So what it tells us that on an average, when you are changing x by 1, y is increasing by 7. So that's what it means. So you change x from 2 to 3, y change from y, like, this is an average rate of change. So x changes by 3, y changes by 21. Okay. So this is how we define the average rate of change. Okay. In graph, what has happened? Let's see. Like in graph, what it is amounts to. So understand this, guys. This height is 4. Okay. This coordinate is 4. So this height is 4. Similarly, this entire height is 25. So this height, okay, from here to here, this is actually the difference. This is delta y. Delta is used to indicate change. So this is yc minus ya. Okay, and this is similarly, this is delta x. You see that this entire length is xa, this entire length is xe. So this is the change in x from 2 to 5. So delta y. So what happens is that if I connect AC point, and then if I look at delta x, which is the horizontal line, delta y, which is the vertical line. So the rate of change is delta y by delta x. So if this angle is, let's say, theta, okay, so this change is what? This change is tan theta. Okay, so this line AC, any line that connects 2 points on the graph is called a chord. Okay, so AC is called a chord. AC is called a chord. Okay, so we can make a rule that rate of change, average rate of change, okay, is equal to slope of chord. It is equal to slope of chord, and this is delta y by delta x. So whatever interval you have chosen, if let's say the chosen interval is x1 to x2, okay, then rate of change. Okay, this is indicated like this. Or no, let's not get into this. So the average rate would be delta y by delta x, or y2 minus y1 by x2 minus x1. So I hope you got till this point, everyone. I hope everything is clear till this. So average rate, I hope this is clear that what is average rate. Now let's talk about the other kind of rate that I mentioned here, which is called the instantaneous rate. Okay, given that average rate is the slope of chord. Okay, um, instantaneous rate is the average rate calculated in a very, very small time interval. So when we talk about instantaneous rate, it is we need to specify an instant. We need to specify an instant. Now, what does this mean? Uh, so, for example, let's say I want to calculate average rate, sorry, instantaneous rate of change when x is equal to 2. Okay, this would mean that I want to calculate the average rate of change for two very, very nearby points, 2 points which are very near to x equals to 2. For example, if I'm trying to calculate rate of change, okay, instantaneous rate of change at x equals to 2, this is same as calculating average rate of change for x equals to 2 and or between, like instead of for we can write between x equals to 2.000. The more zeros you put in between, the better it is. But for the sake of keeping it easy to understand, I'll just put three zeros right now. So if I choose a point which is x equals to 2 and x equals to 2.001, okay, so this is called this would be called the instantaneous rate. And again, the more zeros you put in between, the better answer you are going to get, the more accurate answer you are going to get. Okay, so it basically means that instantaneous rate would be the value of y when x equals to 2.001 minus y when the value of x is 2 divided by 2.001 minus 2. Okay, if we try to do this, it would become 2.001 square of this minus 2 square divided by 0.0001, because this number will become 0.00. And how much is this? Using a bit of algebra, we can write this as 0.0001, okay, multiplied by the sum of these two, which is 4.0001, and then divided by 0.0001. So you can see that you are getting a value which is very close to 4. Okay, 4 point. In fact, I told you that the more zeros you put in between, the more accurate result you get. So if I put 10, 0, 20, 0, 30, 0, this value gets more and more closer to 4, more and more close to 4. So that is what the instantaneous rate is. So instantaneous rate. And let's see what happens to the graph. Like, what is the implication on, what is the impact on graph? So when I say that I want to calculate the average rate between two distant points like this and this, you can clearly see the chord. Now, if I start moving this point closer to the first point, like I started by calculating average rate between 2 and 5, then I say, okay, let me calculate between 2 and 4. Okay, then this would be the chord. Then I would say that, okay, let me calculate between 2 and 3, then 2 and 2.5, 2 and 2.1. So, do you realize that when we start talking about the instantaneous rate, the chord changes into a tangent at 2. Please realize that a chord drawn between 2 points which are extremely close to each other, it will change from a chord into a tangent. Okay, it will change into a tangent, and then the slope of this chord, which has now become a tangent. Okay, this is tan theta. This is slope of chord. This is slope of tangent now. Okay, this is slope of tangent, and this is actually dy by dx. For example, we obtained the value of 4 here. The direct method to do this, instead of actually calculating the average in these two nearby points, we could have done this. If we would have done dy by dx at x equals to 2, we would have obtained, see, dy by dx would have been 2x. Okay, dy by dx would have been 2x. And when we put x equals to 2, see that we are getting 4. So instead of doing all this effort, the direct way to get the instantaneous rate of change is to calculate dy by dx. Okay, so coming back to this, dy by dx is the instantaneous rate of change, which is equal to the slope of tangent, which is equal to the slope of tangent. So, what is the summary here? So, this is dy by dx, which is equals to slope of tangent. Okay. So, what is the summary that you need to learn? Like, what we have learned till now regarding the meaning of differentiation? First is that dy by dx gives you the slope of tangent at a graph. It gives you slope of tangent at a graph. Okay, that is one point. The second point is that dy by dx gives you instantaneous rate of change. It gives you instantaneous rate of change. Okay. Um, Whereas delta y by delta x will give you average rate of change. So please remember these things. Okay, these are the things that you need to remember. Okay, so this is one point. Now we can use this to make further conclusions. Okay, so second conclusion, or we are going to talk about maxima and minima. Okay, so this is an application. This would be an application of this result. The result that dy by dx indicates the slope of tangent. Okay, so I'll write it here. This is application of result that dy by dx is equals to slope of tangent. Okay, so let's say we have a situation in which we are getting graph somewhat like this. Okay, now, in this graph, like this is a function, we don't know what is the dependence. Like there is some function, the graph of which is this. Now, in this graph, there are certain special points that I want you to take note of. Have a note like this point, this point, this point, this point. So these are special points. Okay. I'm pretty sure that intuitively you are also can you can also see that these are special. What is the speciality of this point? This point, like A, B, C, and D. What is the speciality? So A point is highest point in its neighborhood. In this region of the graph, A point is the highest point. So this is called a local maxima. Okay, it is higher than the neighbors on both sides. B would be called a local minima. So A and C, they are called local maxima, and B and D, they are called as local minima. They are called as local minima. Okay, so A and C are local maxima, B and D are called local minima. Now, from graph, I think if I give you a graph and if I ask you to identify the local maxima and minima, you will be able to do that. But is there any mathematical identity of these points? Is there any mathematical identity? So, yes, both of these have got the mathematical identity. So, the mathematical identity. Okay, mathematical identity. Like how can we identify them mathematically? So mathematical identity actually, mathematical identity of maxima and minima. These are also collectively called as critical points. So the mathematical identity of maxima and minima is that, notice, at these points the tangents have zero slope. Okay, that tangents have zero slope. At no other point the tangent has zero slope. See, okay, the slope is positive here, the slope is negative. Okay. So in other words, dy by dx becomes zero. So we can say that if in a graph dy by dx is becoming zero, then it would either be a maxima or it would either be a minima. So that is the mathematical identity of a maxima or a minima. Okay. So this is mathematical identity. Okay, now let us take an example. Okay, for example, let's say y was given to us as let me write x cube by 3 minus 7x square by 2 plus tan x. Okay, somewhat like this. So this is, let's say y is this. Okay, now I want to know that what are the points where a maxima or minima can exist. Okay, so I write this question that identify critical points, that is where maxima can exist and where minima can exist. Okay. Okay. So the solution would be that we say, okay, dy by dx, let's calculate dy by dx. So the dy by dx would be 1 by 3 into 3x square, then minus 7 by 2 into 2x, and then plus 10. And now let's equate this to 0. So on simplification, we'll get x square minus 7x plus 10, which can then be written as x square minus 5x minus 2x plus 10, which can then be written as x into x minus 5 minus 2 into x minus 5, which will then become x minus 2 into x minus 5. And now if we equate it with 0, we come to know that x will either be 2 or it will be 5. So 2 and 5 are the critical points. Mind you, I have not yet identified that whether x equal to 2 is the maxima or whether x equals to 5 is a maxima. All right, I'm not claiming that I've made that clear. They can both be maxima as based on the information that I have right now. They can both be maxima. They can both be minima. One of them can be maxima and the other can be minima. Which is one? Which is minima? Which is maxima? That we have not figured out yet. Okay, but that is for sure that they are critical points. Now, uh, I'm telling you a rule to identify maxima and minima. Like once you have found out the critical point, which one would be maxima and which one would be minima? I'll tell you how to identify that. So, if first derivative is zero and second derivative is positive, then it's a minima. Okay, if at a point, and if this is zero, if dy by dx is zero and second derivative is negative, then it's a maxima. Okay, so please remember this rule. Okay, let's go back to the previous question. So these are the points where the first derivative is zero, and this is the result of first derivative. Let's calculate the second derivative. Okay, let's continue the example. Okay, let's continue the example. So the second derivative would be d by dx of the first derivative. The first derivative was x square minus 7x plus 10. So this would become 2x minus 7. Now, if I calculate the second derivative at x equals to 2, why x equals to 2? Because this is one of the critical points, right? So we have to check the second derivative at these x, not any other x. So at x equals to 2, it will become 2 into 2 minus 7, that is minus 3. It's negative, which means x equals to 2 is maxima. Okay, let's try second derivative at the other critical point, which was x equals to 5. So that would become 2 into 5 minus 7. So that would become plus 3 since it's more than this. So x equals to 5 is minima. All right, so when you plot this graph, when you plot when you plot this function, you will find that x equals to 2 is a maxima and x equals to 5 is a minima. So this is how we figure out the value of maxima and minima. Now, the third point that you need to remember, okay, application in physics. While there are many places uh, where it is useful, okay, there are some common places, like the most common one is that velocity is described as differentiation of position, okay, time derivative, and acceleration is described as time derivative of velocity, which means that it will become time derivative of second derivative of position. So this is where it will be used. We will do it in detail in 1D motion, but this is where it is used. For example, if I tell you that x coordinate of a particle changes with time as, let's say, 3t square, okay, then the velocity of that particle would be 60 and the acceleration would be 6. All right. So, dear students, there was a lot of things that were covered in today's session. I hope there may be times when you would have found it difficult to understand. So I would want you to go back to that part of the video and play it at low speed, listen to each and every word, and try to understand. And most importantly, I want you to try the assignments that I'm sharing with this session. Uh, Trying them out will definitely make you good at differentiation. Right now, your focus should be to learn how to differentiate. how to use that differentiation or when this operation will become useful to you is something that we will cover in different chapters of physics. On that note, I'll bid you farewell for today. You'll see me again in the next session, guys. Take care and continue following this series. Bye bye.